What you'll find is that transverse welds are basically ineffective. They break so early. They're not ductile in shear, and that's just a reality. So they fracture so early that you might as well not put them in. If you look at the AISC rules for bolts and longitudinal welds, those rules are pretty good. They're good. I don't want to qualify. If you have to upgrade an existing structure, rather than look at the AISC spec, which I don't think is good on this point, there's an article in the AISC Engineering Journal that I think gives a better way of handling it. But basically what it's indicating is that, yes, you'll get the longitudinal weld strength. You'll get about 25% of the slip load, assuming you pretension the bolts, and you get on average about 50% of the bolt ultimate shear. Using those numbers gives good results, and that's the basis for the rule that's in the AISC spec at the present time. And there's some recent work, and you have to be aware of the fact that you're checking components successively. Look at the strength of the transverse weld. I'll put it back in. Look at what's left after it fractures, which is the longitudinal weld and the bolts, and then let the longitudinal weld break and look at what's left. Well, what's left is the bolts, and you may have the strength of the bolts may be greater than what you need anyway. So why put the weld? It'll tell you whether you needed to put the welds in. As I say, these problems don't arise very often, but when they do, work on the basis of deformations. Back to real joints. An issue that we have is that usually we can't connect the whole cross section. We can usually connect the flanges. That's the usual condition. But that means that the condition of uniform stress, which we want to attain somewhere a little further out in the member, is disturbed by the flow of forces as it starts in the flanges. So we have to make an accommodation for this. And we do this on the basis of empirically, based on a lot of test results. The ultimate load is 1 minus the eccentricity of the material of the flange relative to the centroid, divided by the length, multiplied by the net area calculated in the usual way, s squared over 4g times f sub u. This means that you have to have designed the joint before you can analyze it. And of course, it means it's iterative, and that happens in lots of cases. But the simplifications that AISC provides work pretty well, and they say if you've got thus and so, W shape with these properties, etc., we'll just give you a factor that works 0.9. Another one is 0.85. I don't know how low it gets, but these are good representations for any case that you're likely to get involved in. A word or two on seismic design. I know some of you were in the session yesterday, so I'm not going to say much. I wish I'd sat in on all of that. Frames are classified in a very simple way as ordinary, intermediate, or special moment frames. And the basis of design is either attaining a certain rotation angle or drift per story. That's not our problem, but it's the basis for design. Now, I want to get to where we are with the connections. So that designer, meaning maybe you or your colleague, is doing the seismic design, and he analyzes the structure to compute the forces. Once he gives us the forces, having looked at FEMA 350 or AISC seismic design, then with 1 or 2 comments, we can say, oh, well, that's how you design the connections. There's no unique feature. When I say the shear strength of a high-strength bolt is whatever, we spent quite a bit of time on that, it's not dependent on the rate of loading. So the fact that we're loading it fast, within the normal attributes, the capacities that I've been describing this afternoon apply to seismic conditions as well as static conditions. So that makes it easy for us at this point. So your colleagues done this seismic analysis, gives you those numbers, and you're on your way with connection design. it is advisable to use pre-qualified configurations, obviously. Here's one for a bolted connection that has been simplified. This is pre-qualified, but I don't show all the details like the continuity plates. So there are welds present. If this is your arrangement, though, then you just go ahead and use the model, the forces that your analysis has shown, and carry on with the design of these connectors, bolts and tension in this case. Here's another pre-qualified one. I used this as an illustration early on. Now, all the bolts have to be pretensioned. You're not, in a seismic condition, you're not given that choice. The Faying surfaces have to be like they would be slip critical. The bearing values that you're going to use, though, are for bolts, which is, there's a conflict there, isn't there? Slip critical and then bearing. We did it differently. We said if it's slip critical, you do thus and so. If it's bearing, you do thus and so. What they're doing, and I think it's a good choice, is they're saying if there are in a moderate earthquake, you will not have slip if you do it designed this way. So you don't do a lot of structural damage. In a major earthquake, yeah, the joints will slip, the bolts will go into bearing, so you're going to have damage, but you won't have a catastrophic collapse. So this part of in this region, the philosophy is different than what we did up to this point, but it looks good. At this time, when I wrote this, it says you can only have normal or short slotted holes, but I think now what they're saying, what I heard them say yesterday afternoon, you can use oversized holes, so you'd have to check that. And they don't want bolts and welds in the same Faying surface, and I wouldn't want them either. You don't get enough ductility out of the welds. I'm going to conclude the session with a design example that will go back through a lot of the stuff that we've covered. I'm using it for two reasons. One is to include a new idea, which is buckling of gusset plates, which isn't particularly anything to do with bolted connections, except that it shows up there so often that we better take advantage of it. But I'm also using it to reinforce what we've been doing, shear strength of the bolt, stuff, block shear stuff, okay? So here's the gusset plate. It's one that was tested. So if you don't like the dimensions, I can't help that. I've got the test results, so we have to use it as the example, and they're reasonable. And so there they are. And there are also measured material properties, which we don't have to walk through. But anytime I need a quantity like plate ultimate load, if I have it measured, I'll use it. If I don't, we'll use the nominal value. And of course, you've got this example in your notes. And the test value was 164 kips. So that's our target. Good practice, good discipline is to set out the issues. Well, what do I need to check? Think about it before you start running numbers. So I'll put the brace force and tension, and then I'll do it in compression. So when the brace force and tension is there, I'll assume it's slip critical, just so I can do the calculation. I probably wouldn't do it that way. So we'll have to calculate the slip load of the bolts, the shear load of the bolts, of course, the bearing capacity of the plates, yep, the block shear, I have to check that, and that's it. When we put the force in the other direction, in the compression sense, as we call it, do I check slip? Well, in principle, yes, but we've already checked it. Do I check shear in the bolts? Yes, in principle, but we've already checked it. Bearing capacity of the plate? Yeah, same comment. We've already checked it. Block shear? No, it doesn't apply. Block shear is pulling out stuff, not pushing in stuff. Okay? So block shear was done for the brace force in the other direction, but does not have to be done, isn't done, would be inappropriate, wouldn't be harmful, but you don't have to do it. And of course we have a new issue, and that's the buckling of the gusset plate in this region. So having set that out, then we can get started. So the slip load, I'm going to calculate it at the factored load level. So it's clean mill scale. which is 0.35. It's a standard hole, so there's no deduction or discount for oversized hole. Discussed that. I know you're looking stuff up in tables, but I'm working it out. I need the area of the bolt, pi d squared over 4. I need F sub u of the bolts, which is 120. They didn't measure that. There are 8 bolts. There are 2 slip planes. The phi factor is 1, and do the calculation. The minimum specified bolt pretension. Now this is review. Look at this line, please. 70% of F sub u. That's where we're heading. We're going to adjust the area, pi d squared over 4, by the 0.75 factor. So work it out. I know you're looking it up in tables, but work it out. 37.88. I think the tabulated value is 39. I use 37.88. So we can go back to the calculation. We've got all the numbers now. I'm not going to talk about each number. When you need help, you can go back through and check these numbers. So we get nearly 30 kips per bolt. We've got 8 bolts, so it's 240 kips is this capacity. We're heading for a test value. I want to compare with a test value, so I'm not putting a phi in, or phi is 1. It's not a design case. It's a checking case for me with a test. Shear resistance of the bolts. Okay, there's the standard stuff. Phi is 1. I'm going to assume there's no long joint effect, meaning the big long joint. I'm going to have to take that 80% that the specification requires, even though I gave you some indication that I thought it was too conservative. So that's what we're taking. We're taking 0.62 of 120. Remember the figure, the little model? It was a physical model. The shearing stuff, the plastification, the shear deformations, is that all rolling back through your head? So 62% of 120, that's fundamental. The 80% is required by specification, and you've heard my comments several times on that already. So 60 KSI, or you're looking it up. You're now part of an elite group. You've got background to material that says, I know that. I know where that came from. I can go back and look at these things. So the shear resistance can now be calculated. Again, phi is 1. So do the number work. There are 2 shear planes, and I'm going to assume there are threads in the shear plane, so I'm going to take that deduction too. This is pretty thin material, so chances are there are threads in the shear plane. So this is 461 kips. So I enter that in on my piece of paper. You're doing it on a spreadsheet, I suppose. We'll calculate the bearing resistance. Phi is 1. It was 1.5 F sub u stuff, or 3 times stuff. The first stuff was shear out of a block of material from the end bolt to the end, or the 3 stuff was the excessive deformation, yielding. And I discussed that. And I discussed the other rule, which is 80% of this one, and my predisposition to use this one. I can't think of one I'd use the other one. So work out the 3DTUS of stuff. We have all those numbers. It's 47.1 kips per bolt. And then work out the 1.5 shear out material. And using measured values where we have them, this is 41.2, which is the governing of these 2 capacities. Multiply that by the number of bolts, which is 8, and we get another value to enter into our matrix, 330 kips. You'll notice as we go through this, this is not a balanced design at all. They had to set it up so they got the failure they wanted, which was buckling. They didn't want the bolts to fail or block shear to happen or whatever. So these other capacities tend to be rather, you'd say, gee, that's too high. I could take 2 bolts out. You might have that kind of reaction. Okay, the block shear. Maybe for most of you, this is relatively new stuff. So what was it about? It was about tension fracture in that ligament and shear yielding up the 2 sides. There's the issue. And even sitting there now, if you didn't have the rule in front of you, you should be able to write that. Tension fracture in that area, shear yielding up those two sides. Okay. So there's what it was, here's what it is, and work out, now it's number work. The net area, I deducted a half hole on each side. You might say, well, maybe I deduct a hole. You'll see that the contribution to the total capacity of the tension part is relatively small. It's mostly the shear, and that's a general statement. And the gross shear area, you can work that out and do the calculations then for the capacity of the two. I'll show them separately so we can see the contributions. From the tension fracture, it gives up first in ductility terms in tension. That's 31 kips. And for the shear, it's 128 kips in round numbers. So the total block shear resistance in round numbers is 160 kips, out of which roughly 30 kips comes from the tension part. There's no reason for me keeping saying that. We would always include it, but it's a smaller contribution. We've accounted for everything then except the what I've called the new issue, and that's the buckling problem. So the issue is buckling or sway buckling in that region. So we've got to check that. How do we check it? Historically, if you're part of the older group, you look at the Whitmore method, which I'll review briefly. It checks yield. It never checked buckling. Well, I don't know why we thought it did. I mean, if you read the original material, you shouldn't have jumped to any conclusion that it checked buckling. And then there's the Thornton method. It does check buckling. Thornton comes along, smart guy, steel fabricator, said this doesn't make sense. It's a buckling problem. So he came up with a reasonably good method, which made a lot more sense, and it checked buckling. And then some other people came along called modified Thornton, and they said, well, we have some test results that we can fit better if we modify something. I'll show you what I mean. So we have those two buckling methods. So the Whitmore method says from that leading pair of bolts, spread the load out at 30 degrees, and then check yielding at that location. This comes from test results too. 30 isn't a magic number, as we'll see in a minute. But this is fine. I would do this check. No problem with this. They went on then, historically, to say, well, I'll check whatever sections I think might be critical and do a beam type check, a P over A plus or minus MY over I. So pick a section, calculate the P force on it and the bending force, and do a allowable stress analysis on it. I wouldn't do that anymore. That's just not the way to do it. It's not the problem. It doesn't predict the ultimate capacity very well. It is usually conservative, but it's not always conservative. And we just can't live with something. We can't stop here. If you say something is sometimes non-conservative, then you have an obligation to find those cases, of course. So Thornton said, calculate these three lengths, L1, L2, and L3. Take the longest. At one point he said take the longest of the three and do a buckling calculation. In another paper he said take the average of the three and do a buckling calculation. I'm going to take the longest. I think, and I'm not wedded to that, but I think it's at this point a matter of engineering judgment. Look at it and say, is most of the plate buckling with the L2 or not? And make a judgment as to whether average would be more appropriate or not. You've got to have some effective length factor too. What's the fixity at the left-hand end of this thing? What's the fixity of there's a ligament that's going to buckle. How is it fixed here? Well, kind of fixed, isn't it? That would be not unreasonable. How is it fixed here? How is it restrained here? I should say it that way. Well, it's not fixed. This whole thing is moving in and out of plane. So it's somewhere in between. And he used 0.65, which is not bad. There's a paper in the current AISC Engineering Journal. If you're designing gusset plates on a routine basis, you might want to have a look at it. It makes a couple of changes to what I'm showing here. I don't have any quarrel with them. So here's our problem, and pardon me, here's our test people. people who tested this said we can get better results if we change that angle to 45 degrees from 30 degrees. Well, they do. But we don't know whether that's generally true. In fact, one of the hypothetical buckling lengths falls off the page, if you like. And I would continue to use L3 in this case. So doing these calculations, and I'll show some calculations in a moment, the ratio Whitmore, Thornton, and modified Thornton are these three numbers, 1.33, 1.67, 1.06, greater than 1 being conservative. And you see the standard deviations. So the Whitmore method is quite conservative, but with a big standard deviation. The Thornton method, which is the middle of the three columns, is more conservative, but with a smaller standard deviation. And the modified Thornton is a good predictor, 106, and a small standard deviation. But remember, they were adjusting for their test results. This doesn't apply across the board. I don't know how good it would be for other cases, but we'll use it for our case. So we'll make some calculations. I just used a scale drawing. The longest length is 9.65 inches. The total width of that base is 19.2 inches. Do a column buckling calculation. This is according to your specification. Use K of 0.65. That's the suggestion, and I don't see any reason to change that. The calculations will be available to you if you want to check them in detail, but there's no connection stuff in this for us, so we'll just carry on. And apply that to the total width, and we get a buckling capacity of 132. And the test ultimate load on this particular specimen was 164. So it's a good predictor. Predicting 132 when actual is 164 obviously is conservative, and we could refine it some more, but it seems to be a good model. The ultimate to predict it here is 1.23. That's higher than it needs to be. So if I was designing a zillion of these connections, I'd spend some time on it. If I was only designing one, I'd stop. It's fine. For Whitmore and Thornton, the corresponding ratios are 1.31. And again, Thornton is quite conservative, 1.80. So there's the summary. And again, I remind you that it wasn't a balanced design. So some of these capacities are not consistent with good design in that some reductions could be made. But you see the buckling load and the test load, 164. Well, a long time ago, being at the start of this seminar, I started by mentioning and commenting very briefly on rivets. That's where we started, and we're going to stop with rivets. And thank you very much for your kind attention, and please stay if you have questions, and safe trip home.